Hello students, I'm going to show you a use for logarithms that you will find very helpful. This week you've been learning about exponential functions and logarithms, and I gave you a discussion assignment that involves the use of exponential functions. I asked you to find out the savings account interest rates from two different banks, and then to plot out the growth of money in that account, assuming a regular deposit, which is to say a fixed amount of deposit every month, and the interest rate being compounded. All right, so some of you have already posted graphs. This is an example of one, okay? Here the interest rate on account 1, which is the red curve, is 0.5%, 0.5%. And remember, you have to express the interest rate in decimal form, so 0.5% is equal to 0.005 in decimal form. Now, can you guess what the interest rate, or rather not guess, but be able to tell what the interest rate is here? Yes, it's 4.3%, and so, which is represented as 0.043. Now, the amount of money in the account is going to grow exponentially. Created the graph in a manner that will enable you to use any value for P0, which would be your regular monthly deposit. So what you need to do in order to use these graphs after you've plotted them is to go to the number of years. The number of years are plotted along the x-axis. And for a given number of years, you can then go up to the curve that you want and then go to the left to read the value on the y-axis. Then take your monthly deposit amount, which is P0. Let's say you put in $100 every month. So multiply that $100 by the y value you read from the curve. So for instance, if we go to this point, it's 4.95 years and a multiplication factor of 60.15. If you fiddle around with this a little bit, you can get it exactly 5 years or whatever number of years you want. All you have to do is to put your cursor over the point and left click the mouse button, and then that will give you the x coordinate as well as the y coordinate. This is good enough for our application over here. So let's say the multiplication factor is about 60. Now with the other bank, which is giving you the 4.3% interest rate, you do the same thing. You go over at 5 years and you click and you get a multiplication factor of 67.49. Well, okay, not bad. The multiplication factor is greater from about 61 to 67. So you can tell that the account, or the money in the second account, which is the green bank here, is going to grow much more rapidly. But to get a real sense for how much more rapidly, it's kind of hard to tell from these exponential functions as plotted here because they're just going up. So one of the things you can do is to sort of zoom in or zoom out, and the graph that I gave you has the viewport locked. You can unlock the viewport by clicking on this wrench icon and uncheck the box that says lock viewport. Okay, now you can zoom in and out. And well, this doesn't really help us a whole lot. Okay, you can see that the difference due to the interest rates from the two banks is growing, and you get a good sense. But now these graphs are taking off pretty steeply. So what do we do? Okay, well, one of the things we can do is to take the log of the functions, and taking the logarithm of function changes an exponential dependence into linear dependence. Okay, now in the exponential functions here, you can see in the exponent here, x is the number of years and n is the interest rate. No, I'm sorry, it's the compounding frequency, and r is the interest rate. And the function grows exponentially because of this factor over here. Well, what we want to find out is, okay, just how much of a difference does the difference in interest rates, or for that matter, the compounding frequency makes? And it's kind of hard to tell from these graphs. So what you do is you go back to this wrench icon. Remember, we wanted to apply a logarithm or take the logarithm of these exponential functions. Now we can do that mathematically and write the equation. We can take the log of the function and then plot the log versus the independent variable here, which is years, with parameters interest rate and compounding frequency. But it's still kind of hard to see. But the effect of taking the logarithm mathematically and then plotting it out is the same as plotting your y-axis on a logarithmic scale. Now this is important. Here the scale along the x-axis and the y-axis are both linear, which means, you know, it's 5 years and then another 5 years or 1 year, and the increment is 1 year at a time. And here in the factor, growth factor, the increment is 5 units at a time. Okay, so but both of these scales are going up linearly. So if I was to convert the y-axis scale to a logarithmic scale, that would in effect be the same as if I took the logarithm of the y values. But instead of going through all of that stuff, there's a simple way of just changing the type of scale. So I go back to this wrench icon, I click on it, and we click on the more options arrow, and here's the y-axis. It shows you right now both x and y are being plotted along linear axes. And so I'm going to take the y-axis and I'm going to convert the scale to logarithmic scale. And look what happens. Now I just move the graph to so that I can easily see it. But now the green and red curves are plotting the logarithm of y. You can still read off the factors that you want that correspond to your x years, the number of years you want, and the interest rates and so forth. So if you left click on a curve, it'll tell you the coordinates at that point. So this is 12 and a half years and a multiplication factor of about 199 over here. These curves are terminating because I limited the number of years that could be put in. But now the difference due to the interest rates and the compounding frequency is much, much easier to see. We can check that by, look, if I move it around, don't look at the end of the curve tip. I guess I really should actually increase this. We will increase the number of years to R2. This is R2, and I was looking at green. So we'll make this... well, actually, what I want to do is to make the x-axis, and we'll make it some 10,000, something like that, all right? And I'm going to move this back. You can learn a few tricks about using Desmos from this too. So now I changed the interest rate, and you can see changing the interest rate makes a huge difference after a certain number of years. Even at a relatively small number of years, you can see the change that's occurring. Similarly, if you change the compounding frequency, let's try that and see what happens. That makes a huge difference, right? So you can see the impact of the compounding frequency and the interest rate by looking at the exponential functions in logarithmic form. In this case, we got the log form pretty easily by simply changing the scale for the graph from linear to logarithmic, and let's go back to linear, and oh, you know, now it's kind of hard to tell. So I hope you find that useful. Try it out for the bank interest rates that you find, and let me know if you have any questions.